We have worked on our major project titled as Ternary Approximate Multiplier. In this project, we have tried to design and implement a approximate ternary higher bit multiplication, which can be utilized in the image multiplication and image sharpening applications of digital image processing. What is ternary logic? Before knowing what is ternary logic, we have to know about the binary logic. Binary logic is the base for all the modern digital commutations, and it is a two-level logic. It utilizes 0 or 1 to represent the data. As we can see the representation of the binary logic level here, it is designed such a way that it can only use two discrete voltage levels to represent the data. Here, as we can see, logic 0 corresponds to the ground voltage level and logic 1 corresponds to the max voltage level, that is VDD. As we have seen that binary logic only utilizes the maximum and minimum voltage levels and does not make use of intermediate voltage levels to represent or store the data. So here the multi-valued logic comes into play. MVL uses more than two logic levels that to represent the data, which makes use of intermediate voltage levels. So one such multi-valued logic is the ternary logic. Using the multi-valued logic, the circuit can process the same amount of data as the binary data in a smaller size, and so that the number of pins, cells and interconnects can be reduced. MVL operations are also superset of standard Boolean logic. So for example, here to store the data 12 in binary data, we require 4 memory cells or 4 transistors. And in the same way, if we represent our 12 in the ternary logic, it requires only 3 memory cells. So one memory cell is reduced from binary to ternary. So that is what here we take the advantage of multi-valued logic. Ternary logic belongs to the family of multiple value logic. Here in the ternary logic uses 3 discrete logic levels to represent the data, that is 0, 1, 2. Using multiple value logic, we can reduce the number of active pins in the hardware, which can also reduce the power consumption as seen earlier. To store the data 12 in binary, we require 4 memory cells, and the same data in ternary, we require only 3 memory cells. That is the advantage we are taking, and using the intermediate voltage levels to represent the data. As mentioned earlier, as binary logic uses only 0 and 1 to represent the data, so huge hardware is required to store. So same data can be stored and processed with a less amount of hardware in ternary logic or multi-value logic. So taking this as our point, we have tried to design a ternary approximate multiplier with a reduced hardware of the existing ternary multipliers. As said, we are going to design a ternary approximate multiplier. Here the term comes approximation. What is approximation? Approximation refers to the process of introducing a known error to the circuit, which results in a minimal error which doesn't affect the functionality of the circuits. Although there will be an optimal error, but there will be a reduction of hardware which helps in the reduction of chip size and interconnections and pinouts. So this approximation has an advantage of chip area and hardware reduction at a cost of minute error percentage when compared to the numbers. Why approximation? That approximation reduces the hardware. That what is the need of approximation? Does it help us in applications? Yes, definitely. Many arithmetic circuits such as adders, multipliers have been proposed using ternary logic previously. But even though ternary logic acts as a alternate for the binary logic, even though ternary logic possesses the high power dissipations and delays. So in order to avoid these, we can approximate the multipliers or adders or arithmetic circuits. So what is the use of this approximation multipliers? It can be used in digital image processing where the degree of accuracy loss is acceptable. That is, our human sensory system has a certain degree of accuracy loss. Like we can't identify the minute changes in the pictures with the human sensories. So in media processing applications, the fundamental operation is a multiplication. As the media processing applications are error tolerant, taking this as an advantage, we tried to design a ternary approximate multiplier with a reduced hardware which acts as an accurate multiplier. First step of designing a ternary multiplier which can be used in image multiplication applications is to design a 1-bit ternary multiplier. So here we discuss about the ternary accurate multiplier. What is accurate? In binary 1-bit multiplier, the multiplication is done using a binary AND gate. So in ternary multiplier, we can't use that because as ternary logic consists of 3 levels 0, 1, 2, and the highest maximum output that can be obtained through the multiplication in the ternary is 2 cross 2 is 4. If the 4 is represented as a ternary representation, it can be represented as 1 and 1. So we have to use both carry and product for the ternary accurate 1-bit multiplier. Here we can see the truth table for the ternary 1-bit multiplier. As I mentioned earlier, it is 2 cross 2 gives the 4, and 4 is represented as 1 and 1 in the ternary representation. So this is the truth table of the ternary 1-bit multiplier. As mentioned earlier, the fundamental blocks for the higher bit multiplication which can be used in image multiplication is a ternary approximate 1-bit multipliers. So here in the first design, we have approximated the product circuits without disturbing the carry circuits. Simply the accurate product circuit is replaced with the ternary AND gate in the approximate design one, and the carry circuit does not disturbed. As we can see the truth table of the approximate ternary 1-bit multiplier design one, the carry term is not disturbed, the carry circuit is not disturbed or not approximated, but the product circuit has been approximated using a ternary AND gate. So as AND gate functionality is to output the minimum of 2 inputs. As we can see, product circuit is resulting the same in this design. In approximate ternary 1-bit multiplier design 2, we have approximated product circuit with a simple ternary AND gate, and carry circuit is negotiated because it consists of all the values to 0 except the case a equals to b equals to 2. So it does not affect much in the when come to the higher bit multiplication. So we have neglected our carry circuit here. So this represents the truth table of the ternary approximate 1-bit multiplier design 2. As we know, multiplication is repetition of addition. When we go for the higher bit multiplication, addition also possesses a very great influence of the complete multiplication. So higher bit multiplication is divided into 2 steps, that is partial product generation and partial product reduction. The partial product generation is done by the ternary 1-bit multipliers, and the partial production reduction has to be done by the ternary adders. So we have to propose an approximate half adder or approximate ternary adder to complete the higher bit multiplication. So we have designed an approximate half adder, ternary half adder, based on the idea that to convert the ternary logic level into 2 logic level, that is using 0 and 2. Then designing the k-maps for that 2 level logic, and then simplifying the k-maps by introducing an error in that particular position. Then utilizing an encoder, we have obtained the end result of the circuit, that is sum. Even using encoder, we have obtained the outputs as 1 as an output, even though inputs are only 0 and 2. In this approximation of half adder, the carry circuit is not approximated, it remains same as the accurate adder. This is the approximate half adder truth table, where firstly we have converted our inputs A and B to the 2-level logic using a NTI and PTI inverters respectively, A and P and B and BP, and based on these terms we have formulated equations for x1 and x2, and we have placed certain error in these particular green blocks in the x1 and x2, and the error is in this particular the two cases have been approximated in this approximate half adder, and the carry is same as the accurate adder. So these are the k-maps for the designed proposed approximate half adders. So here the bold letter of 2 indicates the error. Actually it has to be 0, but we have made it to 2 to reduce the equation. For the x1. Similarly, for the x2, we have reduced the equation by simply replacing 0 of this term to the 2. And these are the reduced equations from the K-map. Based on this, the truth table has been derived. And based on the equations, we have designed our own some half-adder circuit using NVT, HVT, which are the differentiate chiralities CNFETs. And this is the encoder which results are some output from the X1 and X2. And approximate half-adder circuit is same as a accurate half-adder. It does not approximate it. And next, after designing our basic blocks of the multiplier, that is ternary 1-bit multiplier and ternary half adder, next how to approximate our 6-bit multiplication, which has to be used in our image multiplication techniques. So as we know, there are two states in the higher bit multiplication, that is partial product generation and partial product reduction. So here we can introduce an error in a partial product generation or partial product reduction or both. So based on this, we have derived 3 techniques for that, and approximating all the bits of the multiplication may lead to the undesired level of inaccuracy or error, which does not make efficient to use it for the image multiplication and image sharpening. So here for an n-bit multiplication, we results and 2 n-bits results. So the approximation is applied only for n minus bits from the LSB of the result to achieve the minimal overall error. In the approximation technique 1, the approximation is only applied for the partial product generation stage. Like only the ternary 1-bit multipliers are approximated. The ternary half adders or full adders which have been used to reduce the partial products are not approximated. And in this figure, as we see, there are red partial products which means that these are generated using ternary approximate 1-bit multiplier. Rest all the partial products which are represented in the black color are generated using a ternary accurate 1-bit multiplier, and the blocks represent the addition blocks. Like in the adders are not approximated, the approximated adders are not used in this technique. All the adders which are used to reduce the partial products are the ternary accurate adders. See, in the technique 2, the error is introduced in the partial product reduction stage, that is using ternary approximate adders. All the partial products are generated, all the 36 partial products are generated using the ternary accurate 1-bit multipliers, but the reduction stage has used some of the ternary approximate adders. So as we can see in the figure, like every partial product that is represented in the black color are generated by the ternary accurate 1-bit multipliers, whether the dotted red boxes or red blocks represents the ternary approximate adders which are used to reduce these partial products. 3. The approximation is applied at both stages, partial product generation and the partial product reduction stage. So the both ternary approximate 1-bit multipliers are used, approximate adders are also being used. So in the figure we can see that we have a partial products of these red color indicates these are generated using the partial approximate ternary 1-bit multipliers, and the dotted red color boxes also indicate that these are used, the ternary approximate adders have been used to reduce these partial products. These are the complete 3 techniques of the higher bit multiplication, approximation multiplication. And this is the application we have used in a MATLAB to multiply 2 images, and this image represents the output image of result of the accurate multiplication, whereas these results are the output images for the proposed approximation multiplication using our 2 different 1-bit multipliers and ternary approximate half adders. As we can see, as our minute human sensory, we can't find a difference between the accurate multiplication and the approximate multiplication. This is the advantage of our approximate multiplication. That's it. Thank you.